ADOC. All right. In our last class, we started talking about instrumentation amplifier. And this instrumentation amplifier is basically, you would see in most of the electronic devices, power supplies, function generators. Okay, so many electronic devices, you will see this instrumentation amplifier is there. And this instrumentation amplifier, high input impedance at both inputs V sub I sub 1 and V sub I sub 4. And it overcomes, it shows a difference, simply difference amplifier. So we have a difference amplifier here, but instrumentation amplifier has another stage of amplification like here. So look at this amplifier. In this amplifier, we have input. We have one input, so this is our first input number 1, and this is our input number 2. Okay? And here, output number 1, and this is output number 2. Here. So I call this V out 2, and this one I call this V out 1. If you remember, guys, this part is basically a non-inverting amplifier. And also this part. Amplifier. And I actually have a background right here. So these are two non-inverting amplifiers where inputs are applied to the non-inverting input in operational amplifier A1 and A2. Now, this side is the difference amplifier. So whatever input you have and whatever input you have, so these inputs you have V out 2, this is V out 1. So V out, this output, operational, ultimate output, this output, final output, final output is going to be some gain A3, some gain, difference amplifier gain A3, or you can say AID, or AD, so difference amplifier gain, multiplied by difference of these two inputs, which is V out 2, V out 2 minus V out 1. Now, this initial circuit has some major drawback. It amplifies the common mode signals. So it actually amplifies common mode signals. So common mode signals amplification means some noise is going to be amplified as well. And in our last class, I said that we do not want to have noise amplified. So we want to reject, and that is the reason we do need perfectly matched register network. So we do need matched register name. We do need matched register name. For that, what we do, we are going to replace these two registers with a single register. So what we did, in this circuit, I have just redrawn this circuit right here. In this circuit, we replaced these two registers with a single register. Now, okay, tell me, what is the voltage difference between these two terminals? What is the voltage difference between these two terminals? Some idea about that. We have been talking about it for 2 lectures. What is the voltage difference between these two terminals? Zero. Zero. It's a piece of wire. You can think of this as a piece of wire or virtually short. What is the voltage difference between these two terminals? It's going to be zero as well. So therefore, you can think of this voltage VI2, and you can think of this voltage here, VI1 here. So now, if we have reference voltage positive here, negative here, so VID, V input difference is going to be VI2 minus VI1. So this difference, this voltage is going to be whatever voltage we have here, so it is going to be VI2, and this is going to be your VI1. This voltage difference is going to be, voltage across this resistor is going to be VI2 minus VI1. So, and I said that we need perfectly matched resistor here. So we have two resistors here, R1 and R2. So we just replaced R1 and R2 with 2R1. Okay, these two resistors are existing. And we removed the common ground because it actually amplifies the noise, and we do not want that. So once we have this configuration, it's much easier. So what you do, step 1. So we have VID equals VI2 minus VI1, and this voltage minus this voltage, if you can see, if you analyze, like current going through this resistor, current going through this resistor. So if you analyze this non-inverting op-amp, you will see. You guys remember that non-inverting op-amp? So if we have a resistor positive here, negative. So this is V out, this is V input, and this is ground, and this is R2, R1. So V out is going to be 1 plus R2 over R1 times the VI. So this is the equation for non-inverting operational amplifier. Now, if we analyze these two amplifiers, you will see following the same configuration. You will see it is simply 1 plus 2R2 over 2R1. You can simply take out these two to disappear. So it's simply 1 plus R2 over R1 times this input difference, VID. Okay? So we do need this difference. This difference has this expression. And then finally, this output voltage is going to be the gain, which is the difference amplifier that we went through. And that difference amplifier, so that difference amplifier will have a resistor R4 over R3, this R4 over R3. So here we have R4 over R3. We have same resistors. We have same resistors, remember. We have same resistors, R4, R3, here R4, R3. So we have R4 over R3 times the difference between these two inputs here, which is the output from the first stage of amplifiers. So we have that, and then V out 2 minus V out 1, we found this expression. We just substitute it here. So this is the eventual expression for the output of the instrumentation amplifier. So overall gain is going to be this point. So V out over VID overall gain is going to be R4 over R3 times R1 plus R2 over R1. So we have one example. Author has provided nice solution. As I said that in our next class, guys, make sure you pay attention. You don't open the laptop and do something else. So you pay attention the analysis of the section. Otherwise, you will not be able to solve the numerical problems that I will go through next Tuesday. So all the theory I'm going to cover. This example I will cover in our next class in the tutorial session on Tuesday. Now let's go through op-amp integrators. Actually, op-amp integrators, what you did the lab audit. And today the date for the demo, right? And then the report, right? So make sure those who did not show me the demo, make sure you show it to it. And I'm also available. I have class from 3 to 4:15. After that, should be available. So make sure you call me from my office or simply send an email to Max or Wise. They will be able to see your demo. So op-amp integrator, we can integrate signals using operational amplifiers. Now, for simple op-amp integrator, what we do, we simply make use of inverting operational amplifier configuration, which means that the input is applied to the inverting terminal through an impedance. Here, in general, we are going to, instead of resistance, we are going to put impedance, Z1. And on the feedback, we have the impedance Z2. Now, if you look at the inverting operational amplifier, the way we saw that a few, actually last week, inverting operational amplifier, we started with this configuration resistance R1. This is input VI, negative, positive. Negative is connected to ground, positive. Inverting terminal is connected to the output terminal Vout, and this is R2. And we said that Vout is simply negative R2 over R1 times VI. In other words, if the voltage gain is negative, voltage gain equals Vout over Vi, which is basically negative R2 over R1. Now, instead of R1, R2, we are going to put generic impedances. So, which means Z2 over Z1. We are going to put generic impedances. Guys, I have a timer. That I have timer. Make sure raise your hand. I said that 10 minutes for example. Just raise your hand. I'm just going to stop there. Okay. So we have the inverting configuration. Here, instead of resistances, we put impedances. Impedance of impedance connected to the inverting input terminal, and impedance connected from the output to the inverting terminal. And then see, the voltage gain is going to be, for resistor network, the voltage gain is simply negative R2 over R1. Because I said that we are going to put impedance, what you need to do, you need to convert these to Laplace transformation. So the Laplace transformation of the input voltage VI T is going to be denoted with V input S, uppercase S, and Laplace transformation of the output signal as a function of time is going to be denoted with V out of S. So now, because I put generic impedances, we just have to work with frequency domain. Yeah, we have to work in frequency domain, which means that the output represented in frequency domain, in Laplace domain, our output represented in Laplace domain is going to be negative C2 over C1. So because we will be working with capacitors, inductors, in the feedback we will have capacitors, you will see the moment. We have capacitors, so we will be putting impedance instead of resistance because capacitance has impedance, not the resistance. Okay, it has imaginary component. So used in waveform generation, these signals, op-amp integrator are used in waveform generation, analog computation, signal processing, and so on. These are some applications. Let's go through just the analysis part, but the numerical part I will go through in our next class. Look, guys, here we have the input, so Laplace transformation of this input is going to be VIS, and we have the output, and Laplace transformation of the output is Vout. Yes. And we have, what is the impedance? I'm just going to replace this R1 with impedance. Let's call it Z1. What is the impedance of R1, guys? What is the impedance of resistance R1? Just R1. Okay, what is the impedance of this capacitor?
1 over SW.
GC2 is going to be 1 over S. Yes.
Omega C.
Exactly. S is a complex frequency, but when we deal with sinusoidal signal, S is going to be simply J omega. S is going to be J omega, and omega equals to pi. When F is the physical frequency. So the impedance of this capacitor is going to be denoted with Z. C2 is going to be 1 over S C2, and impedance of this R2 is going to be what? I'm going to denote it with Z2 is going to be simply R2. So we can actually redraw this circuit as such. So this is the input in frequency domain. This is my Z1, and then we have negative, positive. Positive terminal is connected to ground, and negative terminal we have one impedance here. I call it C2, and another impedance here. I call it CR2. Actually, I call it C2. So I'm just going to connect this with the output, and the output has to be in frequency domain. It is going to be the output. So now we can see, we can simply have the input C1, negative, positive, and the output impedance I'm just going to call it Z. Just going to call it Z2, and this is my output. So just for notational convenience, so let's call this Z R2 equals R2. Let's call this Z R2 equals R2, and here I'm calling it Z R2, so that I could distinguish. Now this Z2, Z1 is simply R1, and Z2 is simply Z R2 parallel Z C2. So which is going to be ZR2 is R2 parallel ZC2 is simply 1 over give two registers. One of the professors asked ChatGPT that if I have two registers connected in parallel, what is the equivalent resistance? It gave R1 plus R2. So be very careful. We have national conference over Zoom on Tuesday. So it's still yet to be measured. If a stability is given by AI, if you don't check by yourself, do not trust them. So make sure. I encourage that you always have to verify, especially this circuit concept, because you might base it. If you just rely on the stability provided by AI, you might kill a person. You might kill a person, and also, let's say aircraft control system is very complex, and if aircraft's stability is tested by AI, and it says that okay, aircraft is stable and safe to fly, don't get into that aircraft. So always check. So two resistors connected in parallel. The two resistors R1, R2 connected in parallel. So which means that you can actually replace this with one resistor, one equivalent resistor, which is R1 parallel R2, and its resistance, equivalent resistance is 1 over R1 plus 1 over R2. It's going to be R1 R2 over R1 plus R2. So I'm going to do the same thing for impedances. So here R2 times 1 over SC2 over R2 plus 1 over SC2. So we have R2 over S R2C2 plus 1. So we have Z2, which is this impedance, is R2 over S R2C2 plus 1, and we have Z1 is simply R1. So the overall gain is of course S domain. S is complex frequency guys. S domain is complex frequency domain. Our gain is going to be V out of S over Vi of S is simply negative Z2 over Z1, and negative Z2 is R2 over 1 plus S R2C2 over Z1 is simply R1. So it is going to be negative R2 over R2 over R1, R2 over R1 over 1 plus S R2C. So this is the overall gain. So V out of S over Vi of S. You can see this, you can just call it G of S is this. And this is basically the first part of the example. derive an expression for the transfer function V out S over V I of S. We actually did the first part. Show that the transfer function is that of a low pass STI. The STC, single time constant. So if you look at that, if you look at the expression, this is basically transfer. This is basically transfer function. Transfer function G of S is this. And it is, yes, what is the order of S, guys, here? What's the power of S? It's simply 1. It's a first order circuit. It's a first order circuit. So you can simply say that since the power of S in the denominator is 1, which implies first order RC filter, low pass filter. We did that in our last, in chapter 1, low pass filter. And 1 over coefficient of this coefficient of S is R2 C2, which is basically tau, is the time constant. Cutoff frequency of this low pass filter, cutoff frequency F naught is going to be 1 over 2 pi R2 C2. So 1 over 2 pi tau. So this is the cutoff frequency. So we found the cutoff frequency. Now the numerical part of this example. So find the DC gain and the 3 dB frequency. So this numerical part I am going to go through in my next class, just the numerical part. Okay? I have all the derivations, all the expressions. I'm just going to put the numbers in our next class. Okay. Now, because we did the generate part and the example is much more complicated than this circuit, this is a piece of cake. So let's talk about ideal inverting operational amplifier. Ideal inverting op-amp integrator. So where we do not have resistors in parallel, it is simply a capacitor and we have a resistor. Now you can see that impedance, the input, impedance of the input VI is going to be R, and impedance of this resistor is 1 over SC capacitor feedback. So that the output is going to be negative 1 over RC times the integrated version of input. And it provides 90 degree phase shift. It provides 90 degree phase shift. So here I have a derivation, so that the output, the voltage across this capacitor is going to be the initial condition. So this is the initial condition. Initial condition. In other words, initial voltage across capacitor at time 0, at time t equals 0. In other words, Vc at time 0 is simply Vc. Please write it down, sir, so that you understand what is that. So this is the initial condition, and then so the voltage is going to be induced, like voltage across this capacitor. If current flows to this capacitor, voltage is going to be developed, and that voltage is going to be 1 over C, the amount of charge stored in the capacitor from time 0 to t. And then if you substitute the current expression, all what you see is simply V out, the output voltage is going to be simply whatever negative of, if you apply KCL, you see KVL, you see this output voltage is simply negative of VCT, and VCT is just to substitute this expression. So this is what you are supposed to do. So here, see, we have negative VC. I think Stephen was asking that why there was an offset. You remember, Stephen, when you showed me?
I think I was asking about if the integral should be from 0 to t.
Oh yeah. So you had limited integral 0 to t. Now we do not know what is the condition at time 0. Okay. So here we do not know what is the condition at time 0, but what we wanted to see the condition of the voltage across the capacitor at time 0. So voltage across the capacitor at time 0, which is VCT. So you don't know whether the capacitor is discharged completely. Okay? And we do not know what is the initial condition. So when you say VIT, we have VI, right? We have input. So negative 1 over RC, and then integral 0 to t VIT, right? So now if you evaluate this integration, okay, so there would be one part for the integrated version of this input voltage evaluated at time 0, right? Evaluated at time 0. So you do not know what is the initial condition. So that's why what you do, it's an ideal integrator. What you do, you just integrate, and then you do not know when your input signal started. Okay? You just evaluate this integration without limiting factor, and you will see the output is what you are supposed to expect. All right. So as you can see here, output is inverted version of the voltage across the capacitor, and voltage across the capacitor, and this voltage across the capacitor is evaluated as such. Here we have the input voltage. So if you take the Laplace transformation, you will get the, if you take the Laplace transformation, you will get the gain. So I'm just going to quickly write down the gain in frequency. So here it is. So for ideal integrator, we have R1, and then we have negative, positive, and then we have capacitor here, and we have output. So this is C. Let's call this R, and this is VI. out S and VIS. So V out S over VI, function of S is going to be negative GC over R. So it is going to be negative, GC is going to be negative, GC is going to be 1 over SC over R. So it is going to be negative 1 over S RC. So this is the transfer function. This is the transfer function. Now this is negative 1 over RC flow. Negative 1 over SRC. So negative 1 over RC, negative 1 over RC. You see that? So they are same. Only thing is that you have integrated version VIT, and this integration is coming from 1 over S. So 1 over S is basically an integrator. In signals and systems, guys, did you see, did you go to Simulink? There is a block called 1 over S integrator. Did you not go through this? So,
Why did you ever use Simulink?
did you not use Simulink at all? Signals and systems. Probably Dr. Mo will go through this. So, this is MATLAB, guys. Talking about MATLAB, Simulink. So let me show you. I'm not in class, I'm almost done with this chapter. Let me show you. So 1 over S is basically an integrator. Okay? And it is coming right from here. So here we have a blank model. This is not part of the part of this course, but I'm just going to show you that integrator is implemented right here. So if you see this library browser, you can just simply type int. So this integrator block is simply 1 over S. 1 over S means integrator. So if you have a signal, let's say sine. Sine wave, simply sine wave here. So time based, frequency 1 radians per second, and phase is 0. So this is sine wave as the input, sinusoidal signal as the input. And you look at the scope. Okay. So I'm running the simulation for 10 seconds. Same idea, guys. The one that you are using is called PSpice, right? So you see the simulation time, right? So idea basically the same. If you know one software, one modeling software very well, all other software basically centered around that modeling software you can think of. So, for example, in my life, I learned C. C programming language very well. So, I cannot say very well, but significant. I have significant practice in C. And after that, all other programming languages, C++, we never had formally C++, MATLAB, Python, HDL, Verilog, ASP, PHP, JSP, .NET, JavaScript, Java. So all other programming languages is okay. So make sure you understand one modeling software that you are using very well, all other software. So this is okay. Only thing is that you just have to know the underlying theory. That way you know what you are doing. For example, here I know that I'm integrating this signal. This is a sine wave, and I should get the cosine wave. So here I can see sine and cosine on the same page. So here, configuration properties. So here, number of input ports, let's say 2 here. So I connect input and output together, you can see here. So this is my input. And this is the integrated output. If I simply hit run, 2% is compiling. So this is the original signal, and this is the integrated version. This is the integrated version, but this integration parameter has, this integrator block has initial condition 0. So if you simply integrate this signal, you get the integrated output. So my point here is that 1/s is simply an integrator. Okay? So when you see 1/s, you can think of this as an integration operator. Clear, guys? It's not clear? Whenever you see 1/s, which means that there is an integration operator. So let's go back to this expression. This expression you see, from this expression we can get the output. V out of S is going to be G of S times V input of S. So what you see here is negative 1/RC, and then 1/S, and then Vi of S. So now this is an integration operator, so which is simply negative 1/RC. You can think of this as an integrator. So you get V output as a function of time. You simply write integration 0 to t Vi as a function of time. You actually write tau integration, because t is the limiting variable, so the integration variable is going to be different. Tau d tau. So that's what it means. 1/s means it's simply an integrator. You guys understood? The physical meaning of 1/s, guys? Clear? So 1/s is simply an integrator. 1/s is simply an integrator, and you can actually see from right from it's an integrator. 0 to t Vi t d tau. And here we have negative Vc is because what is the voltage, initial voltage of the capacitor at that time. Usually initial voltage when a capacitor is completely discharged, initial voltage is 0. All right, so I have 5 more minutes, actually 7 more minutes. So the frequency response, what you do, you try to find the magnitude and phase in order to come up with frequency response. So we have the transfer function 1 over SRC, and then when you have sinusoidal steady state input, you substitute S equals j omega, omega equals 2 pi f, you get the frequency transfer function negative 1 over 2 pi FRC, and you take the magnitude is going to be 1 over 2 pi FRC, and phase is going to be angle of this quantity. So angle of this quantity is going to be angle of negative 1 minus angle of this one. So angle of negative 1 is going to be, what is the angle of negative 1, guys? So this is, let's say, negative 1 right here. What is the angle of this one? What is the angle of this vector with respect to x? 180. Okay. So that's why negative angle of negative 1 is 180 degree minus angle of this quantity j 2 pi FRC. It is going to be right here. J times 2 pi FRC, which means that this is j omega axis. Okay, so it is going to be right here. What is the angle of this vector? 90 degree. So this vector angle is 90 degree. So 180 minus 90, it is going to be 90 degree. That's how you get the phase difference. Phase of an integrator is 90 degree, which is constant. So regardless of frequency, it is going to be 90 degree. Now the key observation here, the main problem here, there is a problem here. Guys, look. When S equals 0, guys, please pay attention. When S equals 0, S is a complex frequency. When S equals 0, which means that the frequency is 0. Frequency is 0, okay. Tell me, when frequency is 0 of a signal, what does that mean? Is it an AC signal or a DC signal? DC. So DC signal has a frequency of 0, right? Look, very interesting. DC signal has a frequency of 0. You substitute S equals 0. So something over 0 is what?
Yeah.
No, something over 0 is
Oh, that's fine.
infinity. Right? 0 over 0 is undefined. But you have something over infinity. Something over 0 is infinity. So you have 1 over 0 is infinity. Okay? So since you have 1 over 0 is infinity, which means that this gain is infinity. So that is the reason this ideal integrator has a DC problem. Because when S equals 0, when frequency is 0, which means that this gain becomes infinity. And that's why you cannot start with 0 frequency. You have to have some frequency, yes.
So does that basically mean the op-amp will explode?
Oh yes, at frequency gain is infinity, and if you have something, it's not going to do anything. So this problem is called DC problem. And you know the frequency response that you drew in PSpice, okay? You see that you define body diagram. You define the body diagram. You start your starting frequency. You start from 10, right? You don't start from 0. Okay? You don't start. That is the reason actually. You don't start from 0. In case you have DC quantity, you will not see the graph even. So because it's infinity. So when S equals 0, it's infinity. So that is the reason this ideal op-amp has a problem. Ideal op-amp has a problem at frequency 0, which is at DC, and that's why we have a DC problem. And this DC problem is actually we get rid of this DC problem using another integrator called Miller integrator or practical op-amp integrator. So we just have one resistor in parallel with capacitor. Now, when capacitor is 0, you will see that it is, when frequency is 0, okay, when frequency is 0, what is the impedance of the capacitor? At 0 frequency, what is the impedance of the capacitor? At 0 frequency, what is the impedance of the capacitor? Guys? At 0 frequency, what impedance of capacitor CC is 1 over SC. At 0 frequency, what is the impedance?
Infinity.
Infinity. And infinite impedance means that there is no capacitor. So there is no capacitor, but still you will have a resistor that is going to operate just like an inverting op-amp. And that's why if you have a resistor in parallel with this capacitor, at DC you will not have this problem. So previously we had a DC problem, now we actually got rid of DC problem by having this resistor connected in parallel with the capacitor. You understand? And that's why it is called practical operational op-amp integrator. In other words, it's called Miller integrator. And I actually derived this here. We did that for the previous example. Here I said limiting case. When you have this quantity very, very high, this quantity very, very high, it behaves like an ideal integrator, just like previous integrator. When S is very high, when S is very low, which means DC, it operates as an inverting operational amplifier. So, differentiator very similar. Please go through this differentiator at home, and then very similar at home. Homework. Very similar. Okay? And then one more topic I wanted to go through, which is active low pass filter. And this active low pass filter, I'm going to go through this, and I have a numerical problem in our next class. Here. So this is basically a numerical problem. Okay? So active low pass filter, this is not in the textbook. You will not find this in the textbook, but I did that from other textbooks. So it's a numerical problem. I will go through this in our next class. Thank you guys, and all the best. Good luck, guys. When does it start officially? That night? Oh, it starts 10:30? I could go up to 10:30. No?